Welcome to this Yocto project tutorial, where we introduce a widely used and flexible toolset for embedded Linux development. The Yocto project is an open source initiative that provides a comprehensive set of templates, tools, and methods for building custom Linux-based systems tailored for embedded products. Yocto project enables you to build efficient, scalable, and production-ready systems from the ground up. It supports all major hardware architectures, giving developers the freedom to target a wide range of embedded platforms. It's important to note that Yocto Project is not an embedded Linux distribution. Instead, it helps you create one that fits your specific requirements. Yocto Project brings together several essential components to streamline embedded Linux development. At its core is the Open Embedded Build System, co-maintained with the Open Embedded Project. This includes Open Embedded Core, which provides fundamental build metadata, and Bitbake, the engine that drives the build process. Another key component is Pokey, a reference embedded Linux configuration used for testing. Pokey serves as a practical example of how to build a small embedded OS. To ensure reliability, the Yocto project features an extensive testing infrastructure, powered by a BuildBot-based autobuilder. Developers also benefit from a suite of integrated tools, including automated build and testing utilities, processes and standards for board support definitions, and interchange, tools for security analysis, license compliance, and software manifests, SBOM, support in SPDX format. The build system, downloaded with Pokey, includes recipes and layers, flexible components that can be modified, extended, or used as is to create a custom embedded Linux system, tailored to specific needs. With these tools, the Yocto project provides a robust framework for building and maintaining embedded Linux solutions across diverse hardware platforms. Let's explore some of the key features of the Yocto project. First, custom distributions. Yocto project enables developers to create tailored Linux distributions customized to meet specific system requirements. Next, architecture support. The project is highly versatile, supporting x86, ARM, RISC-V, and other architectures, making it adaptable to a wide range of hardware platforms. When it comes to industry applications, Yocto project is widely adopted in medical, automotive, and industrial sectors, providing reliable solutions for embedded systems. The project also benefits from strong industry support, with major tech companies actively contributing to its development. This ensures continuous innovation and long-term improvements. As an open source project, Yocto project is one of the major projects under the Linux Foundation, promoting collaboration, transparency, and community-driven enhancements. Finally, Yocto project offers standard toolchains and libraries, providing developers with a comprehensive set of tools to simplify software integration and streamline development. AMD is proud to be a platinum partner in the Yocto project, a testament to our commitment to advancing open source collaboration and innovation in embedded Linux systems. As a platinum partner, AMD plays a crucial role in the Yocto project, contributing to the development and maintenance of tools and processes that enable the creation of custom Linux distributions for embedded and IoT devices. This partnership highlights our dedication to providing high-performance solutions and supporting the open source community. The Yocto project, under the umbrella of the Linux Foundation, aims to simplify the development of embedded Linux systems by offering a standardized framework and a comprehensive set of tools. Our involvement ensures that the project continues to evolve, incorporating the latest technologies and addressing the needs of developers worldwide. Being a platinum partner, AMD collaborates closely with other industry leaders and the open source community to drive innovation and enhance the capabilities of the Yocto project. This collaboration helps with creating more efficient, scalable, and secure embedded systems, benefiting a wide range of industries. Yocto project offers a framework that provides templates, tools, and methodologies that help developers create a custom Linux distribution that is most suited to the needs of a specific environment. The Yocto project build system leverages scripting languages for build customization. For example, Yocto project recipes can include shell and or Python scripts. Code written in scripting languages can be directly modified in the deployed system, and the changes can be tested without a costly build deploy cycle. In Yocto project, rootfs generation can be modified beyond the customizations possible with PETA Linux. Yocto project has a powerful customization architecture that allows the choice of a wide variety of footprint sizes. Yocto project also provides control over the choice or absence of components, such as graphics subsystems, middleware, and other services. The Yocto project framework, rootfs, includes additional software packages directly from upstream sources and interfaces directly with version control systems like Git. In short, Yocto project offers full control over the build. Yocto project's customizable recipes require some expertise but provide more flexibility, scalability, and long-term maintainability, making it a superior choice for tailored Linux distributions. Yocto project provides a clear and customizable path to production by allowing developers to build highly optimized Linux distributions tailored to specific hardware and requirements. It is well suited for scalable, production-grade environments where control over every aspect of the system is crucial. Yocto project allows for greater flexibility and a smoother transition from development to production with a high degree of confidence in the end product's performance and stability. Yocto project has broad community and industry support with numerous third-party tools, layers, and software packages available. The extensive ecosystem includes contributions from major tech companies and independent developers, making it easier to integrate external software and components into the project. In contrast, proprietary solutions may have more limited third-party support, relying primarily on the vendor's ecosystem, which can limit choices and make integration more difficult. It has an active community of developers maintaining 2,000 plus Linux packages. This is a high-level overview of the Yocto project workflow, including Bitbake, the main engine. Bitbake is a highly efficient task execution system that automates the process of creating a working Linux OS. The workflow begins with configuring 4 key areas: local user information, in which details such as footprint size and machine architecture are configured. Software configuration is done via source recipe files, which specify the package location, license, checksum, and specialized instructions for building. Layers define the hardware and software configuration, including user interface definitions, board-specific configurations, recipes, and image definitions. Distribution configuration specifies the resulting custom distribution items, such as the init system, device manager, and C library. Once configured, Bitbake knows what it needs, where to locate it, and what actions to perform. The source code can come from external or local project source code management SCM systems, or source mirrors. Patches are then applied based on your customized instructions. The shared state mechanism identifies only altered packages for faster compilation. The build result can be packaged into any of the most commonly used package formats. A sanity check is performed on each package to ensure there are no build errors and that it meets the configuration requirements. A directory of all compiled binary packages is created. From this package feed, a bootable Linux system is generated. This system can take several forms, from a raw disk image to a live image that can be booted from a USB memory stick. Additionally, an application developer SDK is created, which includes a cross-architecture compiler, analytical tools, and an Eclipse plugin. Learning Yocto project can be overwhelming for beginners due to its numerous technical terms. Understanding some fundamental terms is crucial, as they are referenced repeatedly in the development flow. Yocto project development consists of several key components: Bitbake, metadata, configuration files, Pokey, and layers. The Yocto project reference manual offers an extensive list of terms and definitions, but in this video, we'll focus on the ones most essential for getting started. The Yocto Project Build tool automates the process of creating a working Linux operating system. Bitbake is the core task scheduler and build tool used in the Yocto project, an open embedded build system. It is often compared to traditional tools like Make, but it provides far greater flexibility and power, particularly for cross-compilation in embedded Linux environments. Bitbake fetches required source code, resolves dependencies, builds the components, and packages the final image. Bitbake is a build tool that interprets .bb recipe files to fetch, configure, build, and package software components. It automatically manages dependencies by constructing a build order tree. Bitbake schedules and executes tasks like fetching source code, configuring, compiling, and packaging. It uses global configuration files and supports hierarchical layering for flexible build environments. Additionally, Bitbake enables both native and cross-compilation, allowing builds for target architectures different from the host system. Bitbake is made up of several essential components. Recipes in the form of .bb files are used to define the necessary steps required to build software components. Configuration files, like local.conf and bblayers.conf, are used to control the build environment. Classes contained within .bb class files contain reusable build logic that can be implemented across multiple recipes. Finally, tasks are predefined steps in the build process that include fetching source code, configuring the build, compiling, and packaging. Together, these components make up the core functionality of Bitbake, providing the necessary tools for efficient and accurate software builds. Metadata in Yocto project refers to the set of input files that define how software is built, configured, and packaged. These metadata files are primarily written in Bitbake syntax and help Yocto project determine how to fetch, compile, and install software. Metadata is structured in layers, which can be combined to obtain various components. Layers are collections of configuration files, recipes, and classes designed for a specific purpose. For example, the Meta Xilinx BSP layer is used for AMD evaluation board support. Yocto project metadata is categorized into several types, each serving a specific purpose in the build process. Configuration files define build settings, machine types, and policies. Key examples include local.conf, which sets user-specific configurations like target machine and parallel builds, and bblayers.conf, which specifies available layers and their locations. Recipes.bb files outline how a package is built, detailing tasks such as fetching, unpacking, compiling, and installing. Class files.bb class act as reusable templates to eliminate redundancy by defining shared tasks and functions. Append files.bb append modify existing recipes from another layer, enabling extensions or overrides without altering the original files. Lastly, layer configuration, conflayer.conf, defines the rules specific to a given layer, ensuring proper integration within the Yocto project build system. Yocto project's metadata-driven approach allows developers to customize the build system efficiently while maintaining modularity and reusability. Configuration files allow developers to customize their Linux-based systems for specific hardware requirements. Several configuration files are in Yocto project, each with its own purpose. The conf directory contains the configuration files that control Pokey and Bitbake. There are two mandatory build-specific configuration files, local.conf and bblayers.conf. One of the most important configuration files is the local.conf file. This file is located in the build directory and controls the build environment, including things like build settings, image settings, and package settings. It can be used to set variables, such as architecture, target system, and distribution version, among others. When we initialize a build environment, a file called build/conf/local.conf is created. This powerful configuration file allows you to control almost every aspect of the build process. The settings in local.conf directly influence how Bitbake compiles your custom Linux embedded OS stack. You can modify these settings or introduce new variables to override defaults from other configuration files. configuration file variables apply globally to every recipe and are collectively referred to as configuration metadata. The main configuration files are processed in the following order: build/conf/local.conf, conf/machine/.conf, conf/distro/.conf. Within local.conf, comments provide helpful documentation, offering insights into available variables and their default values. Another important configuration file is bblayers.conf, which is also located in the build directory. This file sets up the build layers and defines the location of the required metadata. It controls which layers the BitBake build engine uses for building the entire image. This configuration file is crucial as it defines the layers that BitBake should include in the build process. In bblayers.conf, the bblayers variable lists the directories of the layers to be included in the build. The question mark equals operator means that bblayers will be assigned this value only if it hasn't been set already. The backslash at the end of each line allows the string to continue onto the next line for better readability. The top directory variable typically points to the top directory of the build environment. The paths listed, such as meta, meta-poky, meta-yocto BSP, and meta-custom, are relative to this top directory and specify the locations of different layers. Understanding and correctly configuring bblayers.conf is essential for ensuring that the appropriate layers are included in your Yocto project build process. Here are the other configuration files. Site.conf is an optional system-wide configuration file that optimizes builds or specifies cache locations, making it useful for teams sharing a build environment. The layer.conf file is layer-specific and defines how BitBake interacts with a given layer, primarily managing build dependencies within that layer. Distro.conf defines policies for a specific Linux distribution, allowing customization of elements such as the toolchain, package manager, and security settings. Machine.conf is hardware-specific, setting kernel options, bootloader configurations, and other machine-related parameters. Finally, bitbake.conf provides core build settings used across all recipes. This file should not be modified directly. Instead, settings can be overridden in local.conf. Together, these configuration files offer flexibility and control over the Yocto build process. Poky is the reference distribution of Yocto project. It provides a ready-to-use build system based on BitBake and Open Embedded, helping developers create custom Linux distributions for embedded devices. It is not a full Linux distribution, but a framework to build custom embedded Linux systems. Poky includes example configurations, recipes, and tools for testing. Poky consists of several key components that play a crucial role in the software building process. One of the most essential components is BitBake, the build engine that processes important metadata, such as .bb, .bb class, and .bb append files. BitBake's responsibilities include handling task execution, such as do fetch and do compile, among others. Open Embedded Core is another important component of Poky, providing core metadata, such as recipes, classes, and configuration. It also includes fundamental Linux packages. Poky-specific metadata can be found in MetaPoky, which contains Poky's own custom policies and configurations. Finally, board support packages, BSPs, can be found in MetaYocto BSP and are key to testing. These BSPs include elements for testing on QEMU, such as QEMU x86 64-bit and QEMU ARM, as well as for generic x86 64-bit. Together, these four components provide the necessary tools and functionality for building efficient and customizable software packages in Poky. Yocto Project introduces a structured approach to organizing metadata through the layer model, an improvement over the classic Open Embedded project. This model enhances collaboration and customization by classifying metadata into distinct layers. In Yocto Project, each layer is independent yet reusable, allowing a modular way to organize metadata, making it easy to customize and extend builds. Each layer contains recipes, configuration files, and patches that define how software is built for an embedded Linux system. Yocto project layers are categorized based on their functionality and role in the build system. Core layers include Meta, which provides essential metadata from Open Embedded Core, OE Core, Meta Poki for Poki-specific configurations, and Meta Yocto BSP, which includes reference board support packages for platforms like QEMU x86-64 and QEMU ARM. BSP layers contain hardware-specific configurations, such as kernel settings, bootloaders, and device drivers, with examples like Meta Xilinx layer for AMD development boards. Middleware software layers provide additional software stacks, including networking, graphics, and security features. Notable examples are Meta Open Embedded, which offers a collection of useful packages, and Meta Virtualization, which adds support for Docker, Xen, and other virtualization technologies. Distribution layers define policies for specific Linux distributions, such as Meta Poki for the Poki reference distribution and Meta Debian for Debian-based Yocto project builds. Lastly, application layers contain custom applications and their dependencies, often tailored for specific projects or products, such as Meta MyApp for a particular software solution. These layers help structure and modularize Yocto project-based development, ensuring flexibility and maintainability. In the Yocto project, recipes are essential files that define how a particular piece of software is built and packaged. These recipes provide detailed instructions for fetching, configuring, compiling, and installing software, ensuring a streamlined and consistent build process. Each recipe is identified by the .bb file extension, which stands for bitbake recipe. This extension signifies that the file contains the necessary steps and metadata for building the software within the Yocto project framework. First, we have the header, which contains metadata about the recipe, such as the description and license. Next is the source section, which provides information on where to fetch the source code. The build instructions outline the steps to configure, compile, and install the software. Key variables in recipes include srcuri, which specifies the location of the source code, and s, the directory where the source code is unpacked. Depends lists the build time dependencies, while rdepends lists the runtime dependencies. The inherit keyword allows the recipe to inherit common functionality from classes. The Yocto project has a structured directory layout to manage embedded Linux system builds. The build directory contains configurations, sources, cache, and temporary files. AMD modifies and/or adds to this structure by adding a sources directory. Poki is the main repository, while bitbake holds the build engine. Meta includes core metadata, and MetaPoki contains Poki-specific configurations. Meta Yocto BSP offers reference BSPs, and Meta Open Embedded adds extra software packages. Meta AMD Adaptive SoCs and Meta AMD EDF layers add support for AMD Adaptive SoCs and AMD Embedded Development Framework EDF. Meta Virtualization supports virtualization tools like Docker and Xen. Custom layers go in Meta Custom, and Scripts provides helper tools for setup and debugging. This modular structure ensures flexibility for various embedded systems. Now let's look at your typical Yocto project build flow for building custom embedded Linux for AMD Adaptive SoC and FPGA platforms. At the start of the flow, this is done by setting up the Yocto project environment using the repo tool, which is a tool chosen by AMD for EDF flows to manage multiple Git repositories. It is not a requirement from Yocto project. Repo is used by EDF flows to manage multiple Git repositories via a manifest. After repo is added to the system path and Git is configured, it can fetch and organize all sources with a single command, avoiding per repository clones. The EDF Yocto manifests define and pin the required layers for each release, ensuring the correct projects and revisions are synced. Before starting, make sure you are using a supported operating system for Yocto project, and configure Git with your username and email. Then, initialize repo using the provided manifest link to set up all the required repositories. After initialization, run repo sync to pull in the sources. If needed, You can also start a new branch using repo start. Once the repositories are synced, source the setup script to prepare your build environment. Here's an example of the SD card boot flow, showing the steps to build an AMD EDF Linux image. In this flow, you focus on building and packaging the boot image, followed by booting the board. Begin by building the required targets. The first target is the boot image as boot.bin, using supported recipes such as Xilinx bootbin, depending on the machine. By setting the machine variable to the board-specific name and running bitbake, the recipe automatically generates boot.bin. For example, on the ZCU 104 board, this produces the correct boot firmware. Next, build the common EDF Linux disk image using the EDF Linux disk image recipe, which contains the EDF Linux OS. Here, the machine variable is set to the appropriate common disk image definition, such as AMD Cortex A53 Mali Common for the Zynq MPSoC ZCU 104 board. When both the boot.bin and EDF Linux disk image are built, verify the generated files in the deploy directory with the following command. After verification, copy the boot.bin into the wick file using the wickcp command, ensuring the boot firmware and root file system are packaged together. Finally, we flash the wick image to an SD card, insert it into the board, and power on to boot the system with the image we just built. Now let's look at the multi-stage boot flow, where the process begins by building the OSPI boot firmware image. This is done by setting the machine variable to the board-specific configuration and running bitbake with the EDF OSPI recipe. For example, on the Versal VEK385, this generates the required boot firmware. Next, the common EDF Linux disk image is built using the EDF Linux disk image recipe. This step produces the wick image containing the Linux operating system. Here, the machine variable is set to the correct common disk image definition, such as AMD Cortex A78 Mali Common for the VEK385. Once both the OSPI firmware and Linux disk image are built, the generated outputs can be verified in the deploy directory. Finally, flash the OSPI image to the board and boot the board using the EDF Linux image from the SD card, completing the multi-stage boot process. For further study and reference, here are some key resources, which will be useful as you go deeper into Yocto project and AMD adaptive SoC development.